So when I started to prepare this talk, I was wondering what would be the best model for your trajectory in science, the best metaphor. And I recall that, so how does that work? Ah, yes. So your trajectory, as Catherine recalled, it's made of more than 170 publications. I found more than you. 2 books, maybe even 3, as we see. So quite impressive. And then the answer was obvious. Your rocket. Your rocket through the space of math and physics, rushing through the space of math and physics, obviously a multi-stage rocket. So I like this little verse of Cyrano de Bergerac, a poor English translation being given here for the non-French speaking people, me faire par des feux successifs de salpêtre, lancés dans les prés bleus où les astres vont paître. Okay, so Philippe, as I said, a multi-stage rocket, and leaving to Emmanuel and Jérémie and Paul and Rinat the care of talking about the next stages. But before we do that, and also there's the future. I'm sure that there is a very promising future there, but we'll see. Now, before launching the rocket, a lot of preparation is required. And obviously for you had an exceptional familial preparation, familial environment. I mentioned that Philippe's parents were both high school teachers, your mother in humanities and your father in math, in class préparatoire. So certainly it must have been a very stimulating environment. And you have also a brother who took a scientific career. So certainly you had a very stimulating preparation. Also, you can see here the X's. The X's are not a tribute to Mr. Musk. It's rather a reference to leaks, which is, how does that work? Oh, yes. Leaks where, as Catherine recalled, you are admitted with the first rank in 82 at the age of 18 and a half, and you graduate again with the first rank 3 years after as a major. And being a major, first, has maybe a few privileges, but it has also a certain number of duties. And among the duties, you are the flag bearer on ceremonies, like the présentation du drapeau here, or on the Bastille Day, on the 14th of July, when you lead the battalion of the École Polytechnique marching down the Champs-Élysées in front of the President of the Republic, who must have been Mr. Mitterrand, who must have been standing somewhere here watching you. Well, I've been cheating. This is not, in fact, the year of Philippe. I couldn't find a picture of it, but this is the idea. So behind the flag here, Philippe should be there. Anyway, all right. So as I said, the duties, and another duty is that, or constraint, is that when you graduate as the first, or among the first, you are supposed to join the Corps des Mines. So Corps des Mines maybe doesn't speak much to the non-French French people. I should explain, this is a very prestigious institution which is in charge of first training and then monitoring the careers of executives in the higher civil service or in top companies, industrial companies. So at the age of Philippe, typically you'll be either a minister or the CEO of a big company like Mr. Pouyanné, who graduated 1 year after you from the Corps des Mines and who is now the big boss of Total Energy. Anyway, so I hope you have no regrets, Philippe. Good. So, but still, to have the Corps des Mines accepting that you'll be taking a career in science was not an easy matter. I remember that you had to argue, to battle even with the boss of the Corps des Mines. I remember when you came back from this interview, you said, Yes, I got I got it. You had received the green light to start here in Saclay, but it was not easy. You had to be very persuasive. So I would like now to mention a peculiarity of Philippe, which is his rare capacity to do several things together, not in parallel, but really together. I don't know of anyone else who is able to follow a seminar, and by follow I really mean follow, as taking notes and asking questions, and at the same time pursuing his little calculation of the problem of the day. Amazing, amazing. So we'll see many examples of this capacity of en même temps. The en même temps is a reference to our current president, Mr. Macron. This is the favorite motto, or this was the favorite motto of Mr. Macron, but I think you are doing it much better. So as an example, en même temps that you are at the École Polytechnique, in fact, during your military service, you take a degree in math, and en même temps you are starting your duties with the Corps des Mines, you're taking a master in associated physics, and all that with the highest honors. And when I talk about duties of the Corps des Mines, you should realize that it's not purely formal, it's not academic things, taking lectures, but it's also maybe also quite practical. I remember that you had the assignment of installing a ticket system. What did I do wrong? Okay.
Évacuation immédiate de l'ensemble du personnel des bâtiments.
What? Évacuation? You said évacuation? Oh non, c'est pas vrai. So let me finish my sentence. So I was saying Philippe was assigned the work of installing the ticket system in the new subway of La Rochelle, the city of La Rochelle in the province of France. Amazing, right? And so, est-ce que c'est sérieux? Right, okay, so let me go on. We'll see. Where was I? I lost the thread. Oh yes, so at the same time as he's doing all that, he has the good idea of visiting us here in Saclay. And us means, in fact, what I mean by us is the little group working on conformal field theory. So you have Claude Dixon, who was the senior of the team, and Bertrand Duplantier and Hubert Saller, who were interested in conformal properties of critical polymers and percolation. You had Vincent Pasquier, who was doing very strange things involving operator algebras in construction of lattice models. No one understood what you were doing, Vincent, but it turned out to be quite relevant in connection with the 2D CFT. And Andrea Capelli, who had just joined us as a postdoc and started to work with Claude and me on classification of modular advance. And Ivan Kostov would be joining us the following fall for 2 years of postdocs. So you see, it was a small group, still a small group, thank you, but growing rapidly. And so Philippe decides to join us, very good news. He becomes my first PhD student, and within 2 or 3 months, he manages to learn all the important papers to read and understand all the important papers of CFT. And in the fall, with Hubert, the 3 of us, we start working. And as Catherine recalled, the first papers have to do with modular invariance, easing correlators on a torus. This is what we were referring to. And maybe the most notable paper is that one on the Coulomb gas picture in 2-dimensional critical models. But I'm not going to discuss that in detail because I understand that Hubert, where is Hubert? Hubert is there. Hubert will discuss that paper and sort of its legacy in his own talk. Okay, so of that period, I have this unique picture taken during the summer '88 at the summer school of Les Ouches. So we are here on the top of the Parion, which is a little summit of modest altitude, as you can see, nothing very spectacular. And on that picture, you see two young men who look fresh and smiling, while the third guy obviously has difficulties to recover his breath. Right, so after that, we start a new project, and this has to do with a search of graphs. The idea being that with Andrea and Claude, we had found that control theories related to SU2 were classified by ADE linking diagrams, and Vincent had shown how to construct the corresponding integrable lattice models out of the same linking diagrams. So the natural question was, can that be generalized to higher rank groups? And the next case was SU3. So the question was to find, can you find diagrams that are naturally associated with the module invariants that were already partly classified for SU3? And can you also construct integrable models out of these diagrams? So the job had been started by Ivan. Where is Ivan? Ivan has just arrived. So you're just at the right time, Ivan. So Ivan has started the job. Unfortunately, Ivan has just left. So by a matter of few months, we missed your collaboration, Ivan. And that's a pity. Anyway, we managed to write a paper on that. And the search of diagram was a bit empirical. The data that we had was just a collection of weights. We wanted to find diagrams whose adjusted matrix would have a spectrum classified by the same weights, a bit difficult to explain, and also that would support integrable models. So we did manage by a mixture of empirism and what we called CAF, if I remember, computer-assisted FLAIR. So this worked, and in particular, here is a diagram that Philippe managed to construct for the most exceptional case being SU3 at level 21, this comes from what they call a conformal embedding in E7 of level 1. So a fairly complex pattern, but okay, it worked. Very good. So with that, with all this material, Philippe, and yes, I should say that this was just part of the job, but the full list of diagrams were in fact only constructed 10 years ago by 10 years after by Ogneanu. So those are the basic diagrams. Those are the orbifolds that had been constructed by Ivan. And so most of them here were built by us, and Ogneanu somehow managed to complete the picture. So with all this material, Philippe defends his PhD, brilliantly, of course, with the highest honors, of course. And immediately after, as recalled by Catherine, he goes to Princeton. And as recalled by Catherine, he arrived just at the right time. Because in November '89, the three papers of Douglas, Schenker, Brezin-Kazakov, and Gross-Migdal come out, which show how to use matrix models in the double scaling limit to construct models of quantum gravity in 2D. So that's a great excitement. Princeton must have been extremely exciting place to be, boiling with excitement, with competition too, I can imagine, a flurry of papers, but still, the competition doesn't offend you, Philippe, and you manage to write two or three important papers with Kutazov and Distler, and as Catherine mentioned, those papers are really important because you are able to compute correlation functions, which was an open problem at the time. You compute correlation functions for these quantum gravity models coupled to 2D CFTs, And you compute them by two different methods, either by using this approach of matrix models and KDV hierarchies, etc., or by using a more conventional field theoretical method. And the two approaches match, which provides a very important cross-check of the consistency of the matrix approach. So that's those papers have a big impact. And but en même temps, you manage to write yet another paper on the diagram, the search of diagrams now for G2. And en même temps, at the next summer, you manage to, we meet again in Santa Barbara, and together, in a short collaboration, 2 months, we managed to, together with Claude, to do something that I have a good memory of it, an amusing problem of discussing classical W algebras regarded as, how to say, algebras of diffeomorphisms that are consistent with the covariance of differential operators. A bit difficult to explain, but anyway, that's the idea. And 1 year after, you are back to Saclay, and there, as Catherine mentioned, there is again a flurry of papers on very different topics. What I find impressive is that you keep changing subjects somehow. All those within the same area of conformal theories, but different topics each time. So singular vectors, matrix integrals à la Kontsevich, fusion potentials, elliptic genus, Laughlin wave function in the context of the fractional quantum Hall effect, quantum intersection rings in the vein of Witten, computing intersection numbers in modular spaces. Anyway, so, and David, I should mention also, Frédéric Lesage must have been your first PhD student, right? So you didn't wait as long as me to take your first student, obviously. Anyway, what I find quite impressive, as I said, is this variety of topics. And the fuel of the first stage is almost exhausted, and my time too, I guess, so let me proceed. And so in total, I count about 30 papers on CFT, matrix integrals, etc. And as Catherine also mentioned, this culminates with 2 important texts of pedagogical nature, namely this review on 2D gravity and matrix and random matrices, and that you write together with Paul Ginsparg and Jean-Zi Justin. And this review must have been very useful for a generation of young people who wanted to learn this subject. And then we come to this famous, celebrated Big Yellow Book. Now, which is regarded by some as the Bible of conformal theory. Now, Philippe, as you know, yes, you know, I have misgivings about that book. I have serious misgivings. I even have complaints about this book. There is nothing wrong in the book, but there is something wrong on the book, on the cover. And there is something which is a real scandal, which, as everybody can see, this arrow here is wrong. It should obviously be of the opposite orientation, because all the vertices carry these 3 charges. You can see there are these 3 grading, and obviously these 2 opposite arrows are nonsense. So I've been complaining about that for almost 30 years, but to no avail, Philippe. And in fact,
no way I can make it change.
Oh, come on, new edition. And in fact, if I were Ivan, I would complain, because this is not one of our graphs, it's one of Ivan's. So Ivan, you should sue Philippe or Springer Verlag, because they are misrepresenting your work, okay? No, I'm quite serious. That's really very, very bad. And in fact, when you go to the appropriate website, you find a rating of the books. So what's going on there? Whoops. Ooh, what did I do? Anyway, so there is this very good book written with Gernot. But as for the so-called Bible, you see, you have only 4 1/3 stars. You should have 5. And because of this wrong arrow, you lose 2/3 of an. And look at the Chinese edition. The Chinese edition the readers didn't even bother to rate you. And if I'm not wrong, here it says volume 1. So you see what it means.
In the Chinese edition, it's paperback, and there's 2 volumes for 1. It's 1 split in 2.
It's not that they're expecting a volume 2. I wanted to suggest that I wanted to suggest that you work not only on the arrow, but also on volume 2. Since you are so good at en même temps that you carry out your work on Daha and the clusters, en même temps you write volume 2. Anyway, okay, good. So I'm almost finished. So I want to return, this little handle is, I don't know how to get to it. So en même temps, just an example of this en même temps that I was mentioning, en même temps that you are doing other things on totally different subjects, you manage to write a paper on spinning glasses with Cyrano de Dominicis, a paper on the cumulants in an analysis of multi-particle processes in high energy with Jean-Yves Littrot and the co-workers, on the XXX chain with Fedor Smirnov. And even yesterday, I found that you had an exchange with Jim Prop, in which you solve in a flash a question that he was asking. Yeah, just amazing. And in fact, your curiosity extends to bird watching, not only to roses, but also to bird watching. Anyway, amazing. All right, so I've been teasing you a little bit, joking a little. Now let me be more serious and come to a period which was quite difficult for you. And this is what I call the dark years. As many of us know, about 8 years ago, you went through very difficult times. So I don't want to dwell too much on that. It's delicate. I know that you are very discreet on that. Let me only say, Philippe, that the way you confronted the disease, the way you fought it, won the admiration of all your friends and colleagues. And in fact, you introduced a new therapy that doctors don't propose necessarily, which was work. Returning to work after each treatment, however painful, however tiring it was, and with certainly the loving support of Rinat, it worked. You managed to go through. So, and not only you were a subject of admiration, but you were also an example to some people who were in a similar situation, I know. So, Philippe, for all that, for all your courage, and oh yeah, I forgot to say that you even found in those years, you found the energy to participate to the defense of this lab, which was under serious threats. So, Philippe, for all that, for all these qualities, energy, curiosity, courage, your achievement, and your good humor, as Catherine was mentioning, I should have said that too, with all my friendship, I want to say all my congratulations and all my best wishes for many happy returns and many more years of good research. And here is a little souvenir. Thank you.
Okay, so I entitled this talk the Philippe 60 integer sequence because when visiting the online encyclopedia of integer sequences, I came across this sequence, which is I find surprising, and it said Philippe di Francesco 60th birthday sequence. So that's the sequence which I'd like to analyze with you, and I'll give you at least my very personal interpretation of these numbers. So the first number is 60, and clearly it's, that's obvious what it means. We are celebrating Philippe's 60th birthday, but I found there is another interesting interpretation, which is interesting because it demonstrates how important Philippe is to this laboratory, because 60 is also the number of publications of Philippe with other members of IPhT. Okay, so this is, I hope I didn't make any mistake, this is the histogram of the collaborations. And you see that there are lots of collaboration, including some very unexpected ones, like the one, as Jean-Bernard just mentioned, the one with Cyrano de Dominicis on spin glasses, and the one with Jean-Yves Littrot on heavy ion collisions. But okay. And what you see from this histogram is that I've benefited a lot of Philippe's skill. I am this peak, I consider to this peak. So this peak also explains the next number, which is 37, which has two meanings to me. It's first the number of years since Philippe arrived, and I happen to arrive exactly at the same time. And it's also the number of papers that we have been written together since then. And this is a cumulated number of papers as a function of time. And you see there are periods of intense collaboration. And this is what I want to describe. So our first paper was written in 1994. And that's what Philippe looked like at that time. Okay, so he's still working under the supervision of Jean-Bernard, apparently. and was about the entropy of folding of the triangular lattice. Okay, so what was it about? You take a 2D triangular lattice and you want to fold it onto itself, and you ask in how many ways you can do that. And if you look at the 6 triangles around a given point, you see that this is a phantom lattice. I mean, you have 11 possible configurations for 0, 1, 2, and 3 folds. So it's an 11 vertex model. And the questions that people were asking is how this grows with n. So there is a number q here, which was estimated to be of the order of 1.21. And our contribution was actually very simple. We just noticed that if you take a folded state and color the edges of with 3 colors according to their orientation in the folded state in red, green, and blue, and then unfold the object, what you get is 3 coloring of the edges of the triangular lattice, which is equivalent to the folding configuration. So you have so the folded entropy is the same thing as the 3 coloring entropy for the edges of the triangular lattice, which is the same thing as 3 coloring of the edges of the hexagonal lattice by duality, and it had been computed years before. So this is the exact formula. So that was a little later. And then we continued with the folding problems with Mark Bowick and Olivier Golinelli. And the most fancy problem we looked at was this problem with 4 types of fold. I mean, either no fold, or a complete fold, or an acute fold with the angle of a tetrahedron, or a regular tetrahedron, and an obtuse fold with the complementary angle. And you can explain that as, this actually describes the folding of the triangular lattice onto FCC lattice. Okay, so with these 4 types of folds, you have 96 vertices, and we studied this model, and in particular, we studied this model in the presence of some bending energy, which favors the folds, and as a function of this is the proportion of the different types of fold as a function of the bending energy. So here, going this way, you favor the folds, and what you see is that you have 2 transitions, one first order, discontinuous, and one second order, etc. So that was what I would call our folding period. The next period, and the folding periods was basically explain the numbers 11 and 96. So the next numbers are 29 and 145. I'm sure this rings a bell, Philippe. Okay, and this has to do with our Meander period. So, and this is in collaboration also with Golinelli. So a Meander, as you know, is a configuration of a circuit crossing a river via 2 end bridges, and you want to know how many configurations there are for a fixed number of bridges. Okay, and for instance, there are 8 configurations of meanders for n equals 3. That means for 6 bridges. And very little was known at that time about meanders, and the reference paper was that by Landau and Zwankin, who had shown that the number of meanders, which I call Mn, grows like some am to the n, where they even give a bound for am. And then, this is a theorem, but then they conjectured this correction based on the numerics they had at that time. Okay. So what we did was to consider more generally multi-component meanders with several circuits, and with a weight q per circuit, and this defines some am of q and some exponent alpha of q. So we computed many things. For instance, we computed the large Q expansion of this AM of Q, etc. But the most important, the most remarkable result was probably the calculation of this meander determinant. So a multi-component meander is made of an arch system below the river and an arch system above the river, and you glue them and you ask how many components there are. So this defines the matrix of size indexed by the arch systems, which of size Catalan times Catalan, and where the element is simply Q to the number of connected components which you get by just putting this arch system together. And you can ask what is the determinant, and that's the formula for the determinant. And Philippe was able to prove this formula in a very elegant way using the temporally algebra. And as an example of Philippe's incredible, I would say, computational power. I remember coming one day, and in the office, we were sharing an office. He had a huge piece of paper, and I said, "What are you doing?" And he said, "I'm doing the n equals 5 case. That's the 42 times 42 determinant." And he said, "Yes, that's right." And because because Mathematica cannot do it. It's too painful to enter this in Mathematica, so I do it by hand. And indeed, he did it. And you remember, Philippe? Okay. Okay, so that's the formula, and Philippe computed many generalizations, what he calls SUN meanders, etc., etc. So that's a beautiful work, mainly by Philippe. We also introduced semi-meanders. With semi-meanders, it's just a meander with a river with a source. I just talk about that because I want to show you this little program by Golinelli, which is really incredible because it computes semi-meanders numbers with one connected component. But if I give you this problem, you cannot guess at all what it does, but it works. Okay, so based on numerics by Olivier in particular, and also by Ivan Jensen in Australia, it became more and more evident that the exponent alpha was not 7.5, but was something else. And in 2000, with Philippe and with Olivier, we conjectured this formula, which involves this 29 and this 145. Okay, and the explanation, if you want the explanation, is very well summarized in a recent paper, 2023, by Zvonkin, where he quotes our paper, and actually you simply have to read what is written in quotes. So the problem may be interpreted as a pair of two fully packed loops. Each fully packed loop has central charge -2, therefore central charge is -4, and the string susceptibility by KPZ is given by this formula, and the string susceptibility is basically alpha. So this gives the value of alpha. Okay, and that's it. That's about it. It's not complete. Yeah, the last quote I didn't mention, but you can read it. Okay, and we checked. And then we checked we can get, of course, many other exponents for values of Q, etc. And we checked them with Jesper in particular, and they all work pretty well. Okay, so that was the meander period, and all the folding period and the meander period are summarized in this physics report, where we actually can show that even if it's not obvious, there are actually different facets of the same problem, which is the problem of fully packed loops, either on regular or on random lattices. Okay, and I think this explains the number 415. Okay, next is the random map period. So I'm not going to talk very much about that because Jérémie will talk about that. But just I want to mention that this was, the origin of this random map period dates back 1997 with a paper with Bertrand Hénard, where we looked at what are called Eulerian triangulations, which are triangulations for which you can color the vertices with 3 colors. And by a matrix model, a matrix integral, we were able to compute the generating function. It is given by this formula, where U1, U2, and U3 are related to the weights for the different colors, T1, T2, T3. But here, if you are a combinatorialist, you recognize this is a generating function for trees. Okay, so basically, you are starting with the triangulations, and we find 3 trees. Okay, and of course, the question is, where are the trees? And for years, we looked for these trees, and then the answer came from the conjunction of 2 lucky events. First, we hired Jérémie as a PhD student, and then we discovered the work by Mireille Bousquemelou and Gilles Schaeffer on random maps via blossom trees or blossoming trees. And we understood where the tree came from, and from that we started a very rich period, which Jérémie will talk about. I just want to mention the 2 one of our most, I think, remarkable results, which is the distance profile, or the two-point function, which is simply tells you how many points, I mean, what is the profile of distances between two arbitrary random points in a random map, okay? And this is for instance, this run for a map with n equals 50. This is not a simulation, this is the exact, I mean, these formulas are exact, we have the exact formula, so this is the exact histogram. Of course, you can do that for arbitrary sizes up to 200 and compute the continuous limit. Okay, so that's the random map period, and the last period is the Arctic curve period, where we start to look at Arctic curves, and for instance, for tiling problems or non-intersecting lattice path problem. And I think one nice result was that about the 20 vertex model, okay, which is the ice model on the triangular lattice. So I remind you, the ice model is simply you have arrows on the edges, and you have three incoming and 3 outgoing arrows at each vertex. So this gives 20 different possible environments for a vertex. And we put these domain wall boundary conditions, which say simply that the edges enter from the left and the right, and they exit from the top and bottom. Okay, and if you do that, you get this sequence of numbers for n being the size of the square in the middle, to be being n by n. So this is the sequence that you get, and this is an equivalent representation in terms of lattice paths, of non-crossing lattice paths, simply by marking the arrows which are going, I guess, east, south, or southeast. Okay, so we were able to show this equivalence of this 20 vertex model with domain wall boundary condition with a 6 vertex model as follows. You can slightly deform your lattice to be a Kagome lattice just by undoing the vertices of the triangular lattice, and then you can use Young-Baxter to expel the diagonals out of the central square. And what you realize that everything is frozen outside, so what you end up with is actually a 6 vertex model with domain wall boundary conditions, and with these particular weights, 1 square root of 2, 1. So this is the relation between the 20 and 6 vertex models. And the nice thing is that it works also for the 1-point function. So the 1-point function is a refinement where you keep track of the points where the upper pass, this is in the pass formulation, in the pass language, where the upper pass hits the boundary. So it's L, and if it's L, you put a weight 2 to the L, tau to the L, and then you can show that the partition, the 1-point function, which depends now on tau, is the same as that of the 6 vertex model, with this value of, this is defined the same way for the 6 vertex model. So this 1-point function for the 6 vertex model was studied by Colomo and Pronko, and they gave the asymptotic of this function in particular, and from that, and knowing the 1-point function, then you can deduce from the tangent method by Colomo and Sportiello the Arctic curve directly, and that's what we got. So I don't explain what is the Arctic curve, because it was explained already, and these are simulations in terms of path. This is the exact Arctic curve that we computed, okay, and as you see, it works pretty well. And last but not least, something that only Philippe, with his perfect knowledge of this kind of problems, could discover, is that this sequence is also counts domino tilings of a quarter-turn symmetric domino tilings of this particular domain, which is a square, Aztec square with a hole in the middle with the shape of a cross here. Okay, so we can prove that. Of course, we don't know a bijection between the two, but we can show that the numbers are the same. Okay, and that's the kind of thing that Philippe can guess, but of course not many people can guess that. Okay, and so far I think I explained everything. Maybe this one, so for this one I'm sorry I didn't find anything, so sorry, maybe you can help me. And but anyway, thank you very much, Philippe, for your collaboration. It's been a pleasure. It always will be a pleasure, and thank you for your attention.
Okay, so yeah, I'm very happy to be here, of course. So I want to talk about the collaboration with Philippe. So it was perhaps a relatively short period of time during my PhD and a few years after. And after that, Philippe moved on to other topics. So it was a bit of a shock to me, of course, but now I realize that probably he did that for my own good, so that I could develop my own field. So thank you, Philippe, for that. And I will. Okay, let's follow the story. So I met Philippe in 2001. So at this time, so for those of you who have known Philippe recently, so you have to know that he didn't always have his Porsche. At this time, he had a Honda. I'm not quite sure the name of the car. Maybe it's so. This is the car he took me to the canteen for the first time. So maybe not as impressive as a Porsche, but still quite impressive for me. My professor didn't have similar cars at ENS. So okay. So I was happy to see that you could do research and enjoy good things in life too, at least from a certain point of view. And okay, for this reason and maybe other reasons, which I will tell about, it became clear to me that I wanted to do my PhD with Philippe and Emmanuel, and it's fortunate that they agreed. So after we signed the contract, in some sense, I remember a day we were in the office of Emmanuel. So you have to know that at this time, Philippe had an office upstairs on the first floor in French Convention, so that would be the second floor in US Convention. I was having an office on rez-de-chaussée, ground floor, etc. And Emmanuel was at basement level, which we call more nicely in French, rez-de-jardin. So for me, I don't know if it was for this reason, but for me, during my thesis, I found it easier to go to Emmanuel's office because I just have to go downstairs, and I needed an effort to go upstairs to see Philippe, and I was a bit impressed, or I don't know if it was the effort or anything else. But okay, I went to Emmanuel's office, and also Philippe also came, and we met there quite a number of times, but at the first discussion, they just made a list of problems for me to work on. And so I had a dozen problems on the board, some easy, some hard. And I remember that on this list, there was the Razumov-Stroganov conjecture. But wisely, they decided that maybe for a PhD student, it might not be the best thing to start with. Start my, okay. Okay, so we were more, they were more wise, and they said, okay, let's focus on questions intertwining 2D quantum gravity and combinatorics. So it has already been mentioned by several people before. So, of course, as it has been said, Philippe already had a number of contributions in this subject. So here is, for instance, a paper, I don't think it has been shown already, a generating function of fat graphs, where they show that fat graphs, or maps, if you want, their generating function can be expressed in terms of characters. So a remark that has been made several times via the Frobenius formula, and they proceed on that. Also, well, it has this review paper of Di Francesco, Ginsparg, and Jean Justin has been already mentioned. For me, it was really my, more than the yellow book. It was really my livre de chevet during my thesis. So I was one of young people to learn the subject through this review. So it has been very useful. And another contribution which Emmanuel didn't have time to mention, but I should mention that they had a paper, although with Charlotte Christiansen will talk tomorrow, about a problem of 2D gravity, which is Lorentzian gravity. So, okay, it's some sort of random map which has a non-random direction and a random direction, and they found a very nice correspondence with the notion of the concept of heaps developed by Vienno years ago, and we would have liked, of course, Xavier to be here today, but he could not come. But I know that he was extremely impressed by this by discovering that his theory of heaps had applications to 2D quantum gravity. Okay, so now let me go to our first common paper. So I didn't, I really had a kickstart for my PhD because they had several notes. We worked together, we collaborated, and so I just had to choose a subject. I had draft, etc., to develop. Okay, so this led me to the first paper. So maybe the initial FD was given, and I remember the day so here is our first paper, which came a few months after I started, which shows on a problem of hard objects on we call them random lattices or random maps. So it's a random lattice analog of well-known problem in statistical physics, which is the R-square model. And we also studied the dilute version of it. And so what we did is that we were able to solve this model is actually on random lattices. It can be solved exactly through, at the time we were using matrix integral techniques. And we did mathematical calculation, but in the end we got physics results, phase diagram, tricky trial point, etc., discussion of critical exponent, university classes, etc. So I was really loving this subject where I could see relatively simple combinatorics, but giving really non-trivial results of physical nature. Okay, maybe my short anecdote about this would be I did specifically the computation for the dilute model, and so one day I went again downstairs to tell Emmanuel that I did this computation for the dilute model. And then I came back to my office, and 5 minutes later, Philippe went downstairs and he opened my door. He said, you found the result? Very good. Just tell it to me. So he popped it in my office just in a shot. Okay, so this was the first paper, but then there was maybe also a stroke of luck for me, which that after that we looked what we should do, and then there came a revolution, and this revolution was the bijective revolution, and it took the form of a preprint by Philippe Chassin and Gilles Schaeffer. As you see, it was submitted in May 2002. And okay, of course there was the content of the paper itself, but also we really became aware of the work of Gilles that he developed during his PhD thesis for the enumeration of planar maps. You have seen them pictures in Emmanuel's talk, and Gilles really developed a bijective approach to study them by putting them in correspondence with trees. And so it was quite an inspiration because, as Emmanuel mentioned, they already had some results, and that's the first paper we did. Gilles was, in this approach, you are guided by the result of enumeration, the fact that you already know how to solve your counting problem via another technique, which might be more complicated, and then you can guess the bijection out of it. And so Gilles had his own knowledge, but we had a knowledge of matrix models. And in this paper, and you see it was done only 1 month after the preprint, submitted on the archive 1 month after Gilles' preprint, we found a bijection which explained the simple result that Philippe, Bertrand, and Emmanuel found via matrix models. And we didn't stop there. We got another paper 1 month later. So I wonder how we managed to work so fast now in retrospect. So now it was basically giving a combinatorial interpretation to the solution of a one matrix model. Then we took a break because it was summer, and then we continued with hard particles on our graph. So it was in November. And maybe we were a bit competitive at the time, etc. We didn't really ask Gilles whether he was happy that we entered into his field. So Gilles allied with Mireille, and they just say okay, let's. They replied with another paper which generalized what we had before, etc. So then we started to negotiate and to see how not to walk on each other's shoes. After that, let me mention out of this maybe the most important paper, and it's I think it's still my most cited paper. For Emmanuel, I think it's also the most cited paper. I don't know for Philippe. Philippe has more citation for his books, but as a original paper, I don't, one should check. So this is the paper where we introduce the BGG bijection between maps with planar maps with arbitrary phase degrees, and we put them in correspondence with a certain class of trees which we call mobiles. So it was may I say, a straightforward generalization of it's called the Corriveau-Klein-Schaeffer bijection between quadrangulation and well-labeled trees, and we extended beyond quadrangulation to maps with arbitrary phase degrees. And I think it's really not the most difficult paper I wrote. Perhaps it might be the easiest, but it had a simple and nice idea which people could catch, and it was quite useful to study, especially universality properties of random maps, because we could not just study quadrangulation, but more other variants of this model. Okay, so now integrability. We saw it already a few times, but in this context, it made an appearance. So by playing with the tree bijection, you have a new object at your disposal, and then it's better to go beyond just recovering results that you know before the other techniques. Can we do something more? And we realize that the answer is yes. Because there is a parameter in the bijection which you can easily keep track of, which has to do with in maps with a geodesic distance, which has been mentioned. And so we by tree bijection we were able to write an equation of this form, etc. So it's maybe some expert might recognize a variant of a discrete Painlevé-2 equation, but I didn't know that at the time, and etc. And then write down the equation, and then a few days later, Philippe came back to me and said, "Oh, did you know that this equation actually had an exact solution? And here is the solution, etc." So it is expressed in terms of auxiliary quantities, etc. But you take this expression and you plug it back into the equation and you check that it works. But how do you guess such a thing? And okay, well, this is Philippe's magic. So what did he do is that he said, "Oh, this is a nonlinear equation, so let's do something you might do in physics. You linearize. And then you do perturbation theory," and so he did that first order, second order, etc., then arbitrary order, and he noticed that everything can be resummed, and he came down to this formula. So quite nice. The impact of this thing is that with that this is a discrete, and this is a discrete two-point function which Emmanuel has shown as a graph in his histogram in his talk. But by taking a scaling limit, we could actually prove a prediction that was done by Ambjörn and Watagvedi for this quantity, this quantity characterizing pure 2D quantum gravity. Okay, so Philippe didn't just restrict to this. This was for a case of quadrangulation, but we had a host of other equations, more complicated, more terms, more higher order recurrence, etc. But Philippe just tried his favorite method, and in our paper there is this formula. We arrive at, and here is the general formula solving for any model of maps. So, okay, this looks a bit more complicated than the previous one. Actually, I was staring, I was really, it was a trauma for me, this stance we arrive at in this sentence, because actually, okay, Philippe, Philippe had, it was clear to me, but this formula was never clear to me. Actually, we didn't have a proof of it. I mean, so I say it's a prediction. So it's Philippe predictions. Philippe was able to do physics predictions. So we didn't have a proof at the time of this formula. Philippe just guessed it on all cases, etc. He found it follows this general pattern. Actually, okay, it has been... with Emmanuel, we took a while, after 10 years, many detours via other consideration, we found a way to prove this formula via planar maps and continued fractions. So Philippe had inspired us quite a more difficult problem. This, it was just not for us. Let me mention that this integrability phenomenon in the study of distances of random maps, several other authors have been intrigued by this, and I just out of the top of my head, I recall that there is a paper of Mireille, Marcus Kuba, Ambjörn and Bud, Eric Fusy and Emmanuel also have papers where they uncover instances of this discrete integrability phenomenon in models of maps and trees. And also for a few years with Emmanuel, we had, it was a business for us to find observables of random maps which are given by some integrable equations. And so we could, for instance, get the 3-point function, so for law of distance between 3 points. And let me mention, okay, Philippe had moved to other topic meanwhile, so, but he left yet another prediction, which I tried quite hard to prove, but I didn't succeed. Basically, it was the 2-point function of constellation, and it has only been proved recently in a work by Michel Berger, Bertrand Hénard, Emmanuel, and Sofia Nukasi. Just as you see, it has been proved last year. So, okay, let me conclude this talk beyond that by trying to think about what Philippe taught me actually. What is the most important thing he taught me, beyond, of course, doing math, physics, etc. What he told me? Okay. I think it was not something voluntary for him. I don't know if he's conscious that he taught me that. You know, you learn by just a lot by just watching people, etc. And I watched Philippe. The best occasion I could watch him was in the seminar in the Salle Claude Xixton just nearby, the seminar room. And I watched him, and Jean Bernard has already mentioned that he was quite impressive. Philippe, he was able to do his computation at the same time as listening and asking sharp questions to the speaker. So I don't know exactly all his secrets for doing that, but I think I found one. When he was doing that, he just seemed to be happy. I mean, he seemed to be to enjoy what he was doing, and etc. And this is why we put joy in the title of the conference. So I think it's many people discovered that there are two things important in life: love and work and love, and it's better to do both at the same time, and and to love what you are doing, because to love your work, and for that I would like to thank you, Philippe, for learning that to me. Thank you.